Okay. And please, if I will forget recording the lecture many times, so recall me to record, please, when I forget. So, um, okay, I was saying that probability theory wants to deal with the following sentences, like, I don't know, like tomorrow, the probability that tomorrow it will rain is 0.8, or the probability that the next, I don't know, ChatGPT sentence is reflexive is 0.8, no, 0, let's say 0.2. Okay, so these are typical statements that probability theory wants to handle. What's the meaning of these statements? Well, we actually don't care about the meaning. So it depends on the field that you are studying. It doesn't tell, probability theory doesn't really tell you what the above statements mean. So it does not concern the meaning of the above statements, but it rather gives you like a sort of formalism that will be able to treat those statements in a consistent way. It's a little bit, I don't know, for instance, like geometry. Geometry describes like everything in terms of points, but it never defines what points are. Here, probability theory deals with probabilities, but it never defines what do they really mean. Only the relations between what you can do or what you cannot do. It's also in linguistics. I mean, I guess I'm not really a linguist, but for instance, in linguistics, mm, you don't care about the meaning of a sentence, if a sentence is true or not. So you study simply the structure, the relations between sentences, and if a sentence is formally correct. Here we will be able to do formal computations that, yeah, but the meaning of these sentences, if you think about it, is not that easy because, I mean, it is a matter of interpretation, but the theory is quite easy. So let's a little bit analyze these sentences. So um, let me simply summarize what I've said with some sentences. So uh, probability theory gives you a framework in which tells you which tells you how to which operations you can do with the above sentences, let's say. So let's first analyze these sentences. So the first one is the probability that something, the probability of tomorrow it will rain uh, is 0.8. So the first part is so the probability of something is 0.8. So it is a number which tells you sort of the likelihood of this event. So it is intuitive. But if you think if you start thinking about a rigorous way to give to interpret this sentence is a little bit this number, not sorry, not this sentence. This number is not so straightforward, but we don't care about the meaning. We said so. The probability of something is a number, a positive number between 0 and 1, and this something is called usually called an event. So uh, so the sentences have always this structure. There is the probability of something is a number. So the probability is a number, and the something to which the probability is applied is an event. So this is like the probabilistic language. So we need to kind of specify what events are. So let me start with events. So uh, so an event for us will be the following. Will be a kind of a statement, an ambiguous statement. For instance, tomorrow it will rain. It is a statement which is an ambiguous. So events are unambiguous statements that can be either true or false. Uh, but about which you are uncertain. This is I mean, it can be taken as a definition. So what do we mean by unambiguous? Because it can be ambiguous, this sentence. So by unambiguous, we can think that a possible bet, if you want to bet, can be you can decide to which who wins or not. So by unambiguous, we can think we mean that a possible bet based upon the sentence can be decided without question. So this is as simple as that. and we want to compute probabilities of these events. So we can do some operations. We can do some operations on events. So we can we have the following. Okay, let me give some examples. So well, in the previous so the examples we gave here, the events are tomorrow it will rain. Uh, so this is an event. Usually they are denoted by capital letters, and when specified by a sentence, they go in between commas. So this sorry, I couldn't hear. Okay. So and okay. And for the other example, what is the event here? The probability of this event here, the next GPT sentence is reflexive. I don't know. It makes sense, but it's an event. Okay. So these are two examples that we just made, and we can build other events using these operations, which are the operation and, or, and not. For instance, the event E and F is the event, I mean, it's quite easy, is the event that tomorrow it will rain, and the next chat GPT sentence will be reflexive. So we can build also E or F is the event in which either E or F happens. So or we can also say that what is the event not E, which is simply the event that tomorrow it won't rain. So do you have any questions concerning these operations? Should be, I mean, they are quite intuitive. If not, I go on, but please interrupt me if anything is not clear. And we have,
Could I ask something?
yes, yes.
Is this or in question inclusive or not? So if both E and F happen, does the second G still hold?
Sorry, can you repeat? I couldn't.
For E or F,
Okay.
if both E and F happen, is G still true?
Yes, yes, yes. Uh,
Is there like an exclusive or we can
no,
use?
either, maybe it's either, yes. So, so it is like the event either E or F happen. So if both happen, it's still true. So the other one would be like I think it's called symmetric difference. So, but this includes the case in which both E and F happen. And we have some relations between events. So we say that E and F, that E is contained in F if uh, the following happens. Uh, if E is true, then F is true. So, for instance, the event tomorrow there will be a storm is contained in the event tomorrow it will rain. And yes, we write in this case we use this symbol here, and these are the operations we want to we can make. So now the fact is that we want now to put everything in the context of set theory. So now next we are going to use set theory to model events. So what do we do? How do we do this? Well, we need a definition which is very important in probability, which is the one of elementary event. So in general, you don't want to consider every event. So I don't know. This is very important actually to consider all the events. So for instance, if you are paid to conduct some statistical, I don't know, you want to see how many people and visit a shop because you are paid by the shop owner to make some statistical analysis. So you're paid by a shop owner to make a statistical analysis on the people and on the clients. So maybe you want to consider events of the form like tomorrow, like two people will visit the shop. More than 10 people will visit the shop, and so on, so on. But you don't want to consider for instance, in Timbuktu, there will be a storm. So unless the shop is in Timbuktu, but yeah, it is not. Yes, so we restrict to some. We want to consider only some a, a small amount of events of among all the ones you can think of. So we define the events. We define the set of the events that we want to consider will be denoted by this letter, this by this letter, which is contains a small amount of all the events we can think of. We make the following assumption, which is quite important. So that if A and B are events that you want to consider, so uh, are in this set, so that is if A and B, if you want to consider A and B, then also uh, this set is in, you want to consider also A and B. So, so if you want to consider A and B, you want also to consider the event that both A and B happen. So in this sense, we can like choose among the events that we want to consider some particular ones, which are called elementary events, which are the smallest ones. So, for instance, if so, let's take an event that we want to consider, and it can be so. We want to consider uh, one event which is smallest in the following sense that okay, let me write the definition and then I'll explain it. So begin definition. So an elementary event is an event that we want to consider, which is smallest, which is small in the following sense. So if we are able to find another set that we want to consider, if we are able to find a set that we want to consider such that B is smaller, so assume that we find an event that it is contained in A and we want to consider it, then B has to be equal to A. So, so there are no events which are smaller and we want to consider. Simply, in this sense, is as small as possible. Okay, this requires, I guess, some examples. Um, so let's go back to the example of the shop. For instance, um, uh, yes, we wanted to look at events of the form like more than two people, like between 4 and 8 people will visit the shop, or like more than 3 people will visit the shop. So, and so on, so on. So in this case, what are the elementary events? So in this case, for instance, this is not elementary because I can find a smaller event which is contained in the first one, for instance. Let me, it is not elementary because I can find like between 4 and 6 people will visit the shop. This is another event that we want to consider, which is smaller than the first one. So E is not elementary because this event F is such that F is a subset of E. We have found it, for instance, and F is not elementary because, for instance, this uh, do you have in mind what kind of event is contained in F? Well, I don't know. There are some of them. One of it is exactly 4 people will visit the shop. This is an event G, which is contained in F. So F, we want to consider it. Uh, so F is not elementary. It's a little bit abstract. These notions are a little bit abstract, but now we are going to be much more concrete. But uh, okay, the notion of elementary events, it means that are the smallest events we want to consider. I don't know if it makes sense. Uh, so, for instance, in this case, the elementary events can be listed are of the form like no person will visit the shop. Uh, One person will visit the shop. Two people, etc., etc., will visit the shop. These are elementary. If if we are only interested in the number of people that visit the shop, these are elementary because I don't know. I can bet that you will not be able to find an event which you want to consider and is contained into this one, the smallest. Now, they are the smallest because you decided to consider only them, but maybe not that if you're interested also in other stuff like in the gender of the people entering, so also in the gender, um, you can be more precise, and these are not anymore elementary. So for instance, two people will visit the shop is not anymore elementary. So, for instance, it can be written as it can be there are some events which are contained in it, which are like two women will visit the shop, or two men will visit the shop, or one man and one woman will visit. So your elementary events depend on the degree of how precise you want to be. So from now on, we fix the events we want to consider and the elementary events. So we have made a choice. And this is the starting point of every textbook of probability is the following. Is the one of is the definition of sample space. So the sample space omega is the set of every elementary is the set of elementary events. So usually in textbooks you find this definition because this, as we will see now, it will give a really nice model to look at events. So it's quite abstract until now, but it's better, I guess, rather than starting with an omega throw out of the bloom, because now for practical for what it concerns, like games, probability, or algorithm, it's quite clear which will be omega. But for statistics, omega it's usually not clear what is it, and you can, but the events, those are there. I mean, you want to compute probabilities of events, but it is not so clear what the elementary events are. So, do you have questions? Do I need to repeat something? If not, okay. If not, uh, now we can look at events as subsets of omega. How? Um, well, mm, simply we associate to each event E the set of elementary events that compose E. Um, so, okay, this needs an example for sure. For instance, yes, the example that we can make is the usual one. Uh, So uh, a die that has been rolled. So, what are the elementary events in this case? You look only at the faces, at which face the die shows. So the elementary events are like one, which is the event the die shows one, then two, which is the die shows two, etc., and six, which is the die shows six. And the sample space is this one. Okay, do you agree with this? If you look only at the die, you cannot tell the difference between, I mean, these are the elementary events because you decide them to be. And for instance, the event E, which is the face shown, shown is the shown number is even. Uh, how can be written as a subset of omega? Well, this can be written as like the die shows 2 or the die shows 4 or the die shows 6. That is, it is 1 or sorry, 2 or 4 or 6. So we simply, to this event T, we associate this subset. So we write it uh, 2, 4, 6. So we will write that E is equal to this subset of omega. So we make this identification with events from events to subsets of omega. And so we identify an event with the subset of omega that is composed by the elementary events that are contained in the event. The funny fact is that this identification behaves well with the operations that I told you before. So these operations, the operations and or and not become the set operations union, no, sorry, mm, intersection, union, and complementary, which is following one. So, for instance, no, and this is the way in which we use set theory for probability theory. So this is the and this is the starting point of every textbook. But it is only a model. It is not the essence is that you want to compute probabilities of events. And in fact, it is usually the less you refer to the sample space, the better. But there are some sample spaces are pretty good when you want to deal with something that like games like dice rolled, which are for instance, the example that I wanted to make is like a chess match that I have it here. So if you observe a chess match, there is the possible outputs are all the possible the possible outputs are all the possible games you can make. Okay, I didn't copy properly, so let me pass this example. Um, so, for instance, the dice is a very simple has very simple outputs, but a chess match has a huge amount of outputs, and you need some notations to encode everything. For instance, for a dice, we encoded the sample space into these six numbers, which are actually events, so they are not, well, these six events. And here, usually, in chess, you for sure you have seen that there is this notation, and from this you can recover a match. Uh, so this is an element of the sample space of observing a chess match, and it is very difficult to, I mean, it is impossible to write down, in this case, what is omega. We can simply write their elements, but there are a lot of them, and this is called algebraic notation. I didn't know it. So maybe let's do an exercise. For instance, um, okay, you observe two dice. Sorry, no, you observe, so two dice are rolled separately. So first you observe the sum of the faces of the results. First, so write down the elementary events, possibly with a smart notation. Then you observe each die separately. So do the same, write down the elementary events. Uh, okay, so maybe I will leave you some minutes, 10 minutes, 5 minutes to do this exercise. If you finish before, better, but I guess 10 minutes will be enough. So I will be here. So if you have any questions, uh, just ask. And in 10 minutes we will correct these two exercises. So maybe let's correct them, these exercises. So uh, in the first for the first problem, I was thinking actually that you only take note of the sum. So you maybe you cannot see the two dice separately, and you can only see the sum of the faces. I don't know uh, how it can be, but I was thinking about this. So the elementary events in the first case would be like all the possible results. So 2, 3, 4 until 12, where like 1 means actually it means the event that, sorry, there is no 1 here, there is a 2, which means that the sum of the dice is 2, and so on. So these are the elementary events because they are usually called the outputs of the experiment. So if you have simple systems such this one, and you know every like every possible outcome, you simply you simply collect all the outputs, and this will form your sample space. For the second problem, I was thinking that you can look at both die. So you look at them and so you can distinguish the results. So let's write them in this way. There are many ways of writing. So 1, 1, 1, 2, 1, 3, etc., etc., 6, 1, etc., 6, 6. So the first digit is the first dice, is the result of the first die, and the second is the result of the second. So, for instance, 1, 1 is the event, the first die gives 1, and the second gives 1. So in the first case, you are being a little bit less precise because you have less information. And in the second case, you can expand this sample space because you are looking at more precise at the system of the two dice. For instance, the event 2 is equal to the event 1, 1, but the event 3 is equal to the event, sorry, events are subsets. So the event 2 is written in this way. The event 3 is the event 1, 2, and 2, 1, etc., etc. And the event 4 is the event, you know, 1, 3, 2, 2, 3, 1, and so on. So this is a way to, I mean, I guess it makes, you can see that you can be, I don't know, you can change your sample space if you want to be more precise. Simply, this was the scope of this little exercise. So, do you have questions? This exercise. So, if Does it make sense? Right. Usual notation, which is omega. Okay. If not, I can go on. Basically, with events, this is what all that I wanted to say. Now, a break. Yes, this makes sense. Yes, it's a good moment. So let's make a 10 minutes break and see you at 55 minutes. Uh, so let's meet again. Okay, what um now it is okay. Sorry, I guess if I'm not wrong, this is the. I mean, I have problems with the distinct timetables because I'm like 2 hours earlier than you are. So nothing. See you later.